Welcome to The Explainer. AI models are getting insanely powerful, but that power comes with a serious catch. They're huge. Today, we're going to dive into a super clever technique to slim them down, making them way faster and more accessible for everyone. And we'll be using the mighty Qwen 2.5 VL model as our guinea pig.
So let's just start with the problem that I'm sure many of you are facing. We have these incredible state-of-the-art AI models, right? But using them comes at a cost. And what is that cost exactly? It's not just about dollars and cents. It's about accessibility, it's about speed, and it's about energy.
And that brings us right to our first section. We're going to break down the very specific, real-world challenges that pop up when you try to deploy these massive, brilliant models.
Okay, so what are we really up against? First off, these models are absolute memory hogs. They demand super expensive hardware with a ton of VRAM that most people just don't have. Second, they can be slow, like frustratingly slow, which leads to laggy, annoying user experiences. And finally, they are power hungry, which costs money and isn't great for the planet.
So how in the world do we get all the benefits of these huge models without all the headaches? Well, the answer is an elegant technique called quantization. Let's dig into how it actually works.
The easiest way to think about quantization is that it's basically like image compression for AI models. You know how you take a massive, high-resolution photo and save it as a JPEG? Yeah, you might lose a teeny tiny bit of detail that you'd never even notice, but the file size just plummets. It's suddenly way faster to load and way easier to share. That's exactly what we're doing here. And this right here is the secret sauce. The big idea is switching from really complex, nuanced decimal numbers to simple whole numbers or integers. Our computers, our hardware can do math with simple integers so much faster. It's a really simple change on the surface, but it has this profound, massive impact on performance. Now, you've got a couple ways to do this. You can do it after a model is already fully trained. That's called post-training quantization, or PTQ for short. Or you can actually build quantization right into the training process. But today, we're going to focus on a really powerful and popular PTQ method called GPTQ, because it's specifically designed to shrink these giant models while keeping their accuracy incredibly high. All right, enough theory. Let's get our hands dirty and see how this all works in practice. We're going to walk through a Python script that does exactly what we've been talking about. Okay, look, we're not going to do a line-by-line slog through this code. Instead, let's just focus on the big picture, which really boils down to three main steps. First, as you see here, we gather our tools. Think of Torch and Transformers as your workbench for handling the model. But the real star of the show is GPQ model. That's the specialized power tool that's going to do all the heavy lifting for us. The second step is to create a game plan. We're setting the rules for the quantization process. We're telling it, hey, convert the model's weights to 8-bit integers and do it in these small, manageable groups of 128 for better accuracy. Now that sim equals false part, that's really interesting. It tells the tool to use something called asymmetric quantization. It's like giving it a flexible, sliding ruler instead of a fixed one, which allows for a much more precise fit when converting the numbers. And that usually means a more accurate final model. And the third phase is the real workhorse, this loop. This is where the magic happens. A model's weights are kind of like its brain power, and they're stored in these huge tables of numbers called tensors. This loop just methodically goes through every single one of those tables, finds the absolute best way to convert those decimals into simple integers, and then it makes the switch. It's just systematically replacing the old, bulky data with a new, lean, efficient version. Finally, the main function just pulls everything together. You load the big, original model, you run our shrinking function on it, and then you save the brand new, much smaller version. And that's it. It's a really straightforward workflow that gives you a model that's ready to run on way less powerful hardware. So now that we've seen the code, let's pop the hood and take a closer look at what's actually happening inside the GPTQ method itself. This is where things get really clever. What makes GPTQ so smart is that it doesn't just crudely convert the whole model at once. No. First, it divides all the weights into these small independent groups. Then, for each of those tiny groups, it calculates the perfect conversion formula to minimize any loss of information. It's this super precise group-by-group optimization that lets GPTQ preserve so much of the model's original intelligence. So here's a little peek at the data before we touch it. It's just a sea of these very specific, high-precision decimal numbers. These are the model's weights, and each one is a very nuanced instruction that takes up a lot of memory and processing power. And look at that. This is the transformation. Those same values are now represented by simple 8-bit integers. They're way smaller to store, and critically, they are so much faster for a computer to do math with. It's a night and day difference.
All right, let's bring it all home. Let's talk about the key takeaways and practical things you'll need to remember when you go to apply this amazing technique to your own projects.
Okay, this is probably the most fundamental decision you're going to have to make. You're navigating a trade-off. If your number one goal is keeping the highest possible accuracy, you'll probably want to stick with 8-bit quantization. But if you need the absolute smallest, leanest model you can get, you can be more aggressive and go down to 4-bit, but just know you might see a tiny little dip in performance.
Think of this table as your control panel. These are the main dials you can turn to get the result you want. Bits and group size are your primary tools for balancing that accuracy versus size trade-off. Learning to tweak these settings will help you get the perfect model for whatever you're building.
And here are just a couple of pro tips to help you get the absolute best results. First, using something called calibration data, which is really just a small sample of the kind of data your model will be working with, can help the quantizer make smarter decisions and give you a more accurate result. Second, it's pretty standard practice to only quantize the main model weights and leave other things like biases alone to avoid any weird performance problems.
At the end of the day, quantization is really an enabling technology. It takes these state-of-the-art AI models and makes them accessible enough to run on laptops, phones, all sorts of everyday devices. What's so exciting is that this democratization of AI just unlocks a whole universe of new possibilities. Which brings us to our final thought for you. Now that you know how to make AI lean and mean, what will you build?